This video covers closure properties for context-free languages. The first one we'll cover is the union. Context-free languages are closed under union. So this means you can have two context-free languages, and if you take the union of those two languages, it will also be context-free. Let's show this using two languages, L1 and L2, described by two grammars, G1 and G2. Assume that V1 and V2 are disjoint. That means the symbols in V1 are not equal to the symbols in V2. Don't forget that V1 is the set of non-terminal symbols, right? Basically the states. T1 is the set of terminal symbols. S1 is the starting production, the starting state, and P1 is the set of productions or transitions. We're going to consider the following grammar, G3, and I'm going to show that G3 is actually the union of G1 and G2, and therefore the language described by G3 is the union of language 1 and language 2, and they're all context-free. So G3 has the set of non-terminal symbols V1 union V2 union some new symbol S3. So it includes all of the non-terminal symbols from grammar 1, all the non-terminal symbols from grammar 2, as well as a new symbol, S3. The terminal symbols are the combination of terminal symbols from G1 and G2, so it's T1 union T2. We have a new starting symbol, S3, and we have a new set of productions, P3. S3, like I said, is not in V1 or V2, so it's a new symbol. And P3 is going to be our set of productions from grammar 1, so P1, along with our productions from grammar 2, P2, and one new rule. S3 goes to S1 or S2. What does this actually do? It allows this grammar to generate words from grammar 1 and from grammar 2. Because our new starting symbol S3 can go to the starting symbol for grammar 1 or the starting symbol for grammar 2, this grammar now produces words both in language 1 and language 2, using grammars 1 and grammars 2. G3 is a context-free grammar. It follows all of the requirements for a context-free grammar, and therefore the language of G3 is a context-free language. And in fact, the language produced by G3, or L of G3, is the union of L1 and L2. If we take a word from language 1, S3 would go to S1 and it would eventually produce W. So that produces all words in language 1. Let's take a word in language 2. S3 would simply just go to S2, which would then eventually produce this word. So S3 is allowed to go to S1 or S2, and therefore G3 produces words in language 1 and words in language 2. Since V1 and V2 are disjoint, that means they don't have any common symbols. S1 producing W can only include productions from P1. And so in that situation, that word is in language 1. And similarly, if you have a word that is produced by starting in S2, you can only include productions from P2. And so the word is in language 2 in that case. Therefore, because we can produce both words from G1 and G2 by simply starting in S3 and either going to S1 or S2, the language of G3 or L3 is equal to the union of L1 and L2, and therefore context-free grammars are closed under union. A more intuitive way to understand this is using NPDAs. So let's assume we have two machines. We have language 1 described by machine 1, an NPDA, meaning L1 is a context-free language. We have L2 described by M2, an NPDA, which means that L2 is a context-free language. In both cases, we have our machines. Each machine has a starting state, S1 for M1, S2 for M2. And all we need to do is create a new starting state, S3, that can either go to S1 or S2, and we'll have our new machine. So we've generated a machine, M3, an NPDA, that has S3, which allows it to go to either S1 or S2, producing words from language 1 and language 2. Therefore, context-free languages are closed under union. The next one we'll cover is concatenation. Context-free languages are closed under concatenation. That means you can take two context-free languages, and if you attach them one after the other, that is also a context-free language. So let's consider our languages once again, L1 and L2, described by grammars G1 and G2. Again, assume V1 and V2 are disjoint. We're going to create a new grammar G4, and G4 is actually going to show the concatenation of G1 and G2, and we're going to show that this is context-free as well. So G4 is V1 union V2 union S4. So we're adding a non-terminal symbol S4, which is going to be our new starting state or starting symbol. And then we have our terminal symbols, which are a union from T1 and T2, and we have a new set of productions P4. S4 is a new symbol, so again, it's not in the union of V1 or V2. And P4 is going to be our set of productions from P1, P2, and a new production, S4, which goes to S1 followed by S2. That is S2 concatenated with S1. Therefore, the language of G4 is actually the language of G1 concatenated with the language of G2, which is L1 concatenated with L2. This makes a little bit more intuitive sense, again, when we describe them in terms of machines. So we have L1 described by M1 and L2 described by M2. We have our starting states S1 and S2. So we create a new machine, M4, that has a new starting state, S4, and S4 goes to S1. And then once machine 1 is complete, that will go to S2. And once M2 is complete, then a word will be produced. So our M4 is just an NPDA, which describes G4, and therefore G4 is a context-free language, describes a context-free language. And so we've shown that context-free languages are closed under concatenation. Context-free languages are also closed under star closure. So we only need one language for this, and we're going to use language 1, described by grammar 1. We're going to consider a new grammar, G5, which is going to represent our star closure of G1. So our non-terminal symbols will be V1 union with the new symbol S5. S5 will be our new starting symbol. We still have our same terminal symbols, T1, we have our new starting symbol S5, and we have our new set of productions, P5. Here, S5 is not in V1, and so it's a new symbol, is all that means. And we have our new set of productions, P5, and P5 includes all the productions from P1 and one new production. S5, our new starting symbol, can either go to S1, S5, which would basically concatenate the language with itself, which is what star closure is, or lambda. Because star closure includes the empty string, we have to be able to go straight to the empty string to make sure it's included in the language. This is pretty easy to follow. So the language generated by grammar 5 is the language of grammar 1 star, which is L1 star. All that's happening here is that we have our new start symbol S5, and it just repeatedly generates words from L1. Again, we can describe this in terms of an NPDA. So we have L1 described by NPDA M1. It has a start symbol S1. We create our new machine M5, which creates a new start symbol that can either go to S1 and then cycle back to S5, or it can go to lambda. This is an NPDA, and it describes our language L5, and therefore L5, which is the star closure of L1, is a context-free language. And therefore, we've shown that the context-free languages are closed under star closure. Intersection is a different thing altogether. Context-free languages are not closed under intersection. That means if you take two context-free languages and you take the intersection of that, it may not be context-free. Before I can cover the proof for context-free languages not being closed under intersection, we have to present a language that is not context-free. This is the language that we're going to use. L equals A to the N, B to the N, C to the N, where N is greater than or equal to 0, is not context-free. This language is simply A's, B's, and C's, where the number of A's, B's, and C's are the same, and A's precede B's precede C's. We need the pumping lemma for context-free languages to show this is true in a real rigorous way, but we can kind of intuitively think about it, and we can construct an NPDA for L. So let's think about the NPDA for L. We can do it just like we had with A to the N, B to the N, where each time we read an A, we push an A onto the stack, and that counts our A's. Each time we read a B, we'll pop an A from the stack, and this will allow us to match our A's and B's. Now, what do we do with C's? We have to ensure that the number of C's is equal to the number of A's and B's, but now there's nothing on the stack. So we don't even really know what to do. We don't know what we're counting to, and we have no means of dealing with this. So it's not context-free because we can't generate an NPDA. You may be thinking, well, this is only one try. We only tried one NPDA. But if you think about it a little bit more, you'll realize that it's really impossible. But of course, this is not the way to show that a language is not context-free. You have to use the pumping lemma to do that. We are covering that in the next video. So just go with me on this one. A to the N, B to the N, C to the N is not a context-free language. So let's consider these two languages to show that the intersection of two context-free languages is not closed. L1 equals A to the N, B to the N, C to the M, and L2 equals A to the N, B to the M, C to the M. L1 is basically just the number of A's equals the number of B's, and there can be any number of C's, including 0. L2 is similar. There can be any number of A's, including no A's, and then the number of B's and C's must match. Both of these languages are context-free. You can generate NPDAs for them. It's pretty simple to do. The first one would be generating an NPDA for A to the N, B to the N, and then allowing any number of C's after that. The second one would be allowing any number of A's and then using the same NPDA for B's and C's. Another way to show this is that L1 is the concatenation of two context-free languages, which we've already shown is context-free. Similarly, L2 is the concatenation of two context-free languages, which again, we've shown means that L2 is context-free. So now that we know that L1 and L2 are context-free languages, let's take the intersection of these two languages. We'll get L3 as a result, and L3 is not context-free because the intersection of these two languages is A to the N, B to the N, C to the N, where N is greater than or equal to 0. And I just told you that that's not context-free. So L1 is A's and B's must be equal in number and C's can be any. L2 is A can be any, B's and C's must be equal in number. So the words that are in both of those languages are the ones where all three letters are equal. That is where N number of A's, B's, and C's, where N is greater than or equal to 0. And so the intersection of these two languages is A to the N, B to the N, C to the N, which is not context-free. Therefore, we've shown that context-free languages are not closed under intersection through one example. It is true, however, that the intersection of a regular language and a context-free language is context-free. So let's consider L1 a context-free language and L2 a regular language. The intersection of these two languages is context-free. We're going to show this by generating an NPDA for L1 intersection L2. We're going to use the NPDA for L1 and the DFA for L2. M1 is going to describe our NPDA for language 1. We have Q, sigma, lambda, delta 1, Q0, Z, and F1. Q is going to be our set of states, sigma is going to be our alphabet, lambda is going to be our stack alphabet, D1 is going to be our set of transitions, delta 1 is going to be our set of transitions, Q0 is going to be our starting state, Z is going to be our starting stack symbol, and F1 is going to be the set of final states. This NPDA accepts L1. M2 is going to be our DFA that accepts L2, where we have our set of states P, our alphabet sigma, which is the same, our set of productions D2, our set of transitions delta 2, P0 is going to be our start state, and F2 is going to be our set of final states. So we are tasked with constructing a PDA or an NPDA M hat, which has states Q hat, alphabet sigma, stack alphabet lambda, delta hat is going to be our set of productions, our set of transitions, and Q0 hat is going to be our starting state, Z is going to be our starting stack symbol, and F hat is going to be our set of final states. What this NPDA is going to do is it's going to simulate M1 and M2 running in parallel. So it's going to take an input and it's going to run it through M1 and M2 at the same time. And if they both end up in a final state, then M hat will end up in a final state and the word will be accepted. So what is Q hat? Q hat is going to be the set of productions, the set of states from Q cross P. So it's going to be combinations of states from Q and combinations of states from P. Q0 hat is going to be Q0 and P0. So we're going to start in the start state for M1 and the start state for M2. F hat is going to be productions. F hat is going to be states from F1 and F2, combinations of those two. That's what the cross means. And we're going to define delta hat, that is our productions, such that if we are in state QI, we read an A and there's a B on the top of the stack, then we transition to QKPL, which is our new state, and we push X onto the stack, if and only if the transition delta 1 QIAB results in QKX is in M1 and reading A and being in state PJ results in being in state PL in the second machine. So that's a lot of mumbo jumbo. We're almost there. I'll explain it in English, I promise. Also, we want to keep in mind that if A is lambda, then PJ equals PL. So that just takes care of the non-determinism in our DFA. So what does this actually mean in English? Let's take a second to think about this. So what's really happening here is our states are no longer single variables. They're not single letters. Like our states in M1 used to be Q0, Q1, Q2, and so on. Our states in M2 used to be P0, P1, P2, and so on. Now our states are going to be combinations of a state in M1 and a state in M2. So that's what you're seeing here, a state in M1 and a state in M2. So what happens now is we're in this combination state. We read an input A, we pop a B off of the stack, whatever the A and B may be, right? And then what do? Well, we go to QKPL, which is a new state, which is a combination of our old states, and we push an X onto the stack. But we only do that if this is a valid transition in M1. So if we're in M1 and we're in state QI, we read an A, pop a B, and we can go to QK and push an X, then that's what we will do here. But only if we also transition from PJ to PL after reading an A. So what this really means is that if we're in a particular place in M1, we read a particular input and we pop a particular symbol and we transition appropriately, and the same thing goes for M2, except for all we're doing is reading, we're not pushing and popping, then if both of those things are valid transitions, then we can have the same transition in our new machine. It's just a combination of these two in one. And also we need to be able to handle the fact that the input might be nothing, which a DFA normally can't handle. And so what happens is we just have a self transition, if that's the case. Take some time and think about this because there's a lot of mumbo jumbo going on here. But what's really happening is we're creating a hybrid machine. MHAT is a hybrid machine where M1 and M2 are basically baked in. But instead of just transitioning from one state to the next, we're kind of keeping track of parallel processing in M1 and M2. So if we had an initial state Q0, P0 for M1 and M2, now we have our Q0 hat, which includes both of those. And if M1 transitions to Q1 and M2 transitions to P1, then our new machine transitions to Q1, P1, which is our new state, which is a combination of states from M1 and M2. So just think about that, because I know there's a lot going on this slide and there's about to be even more. But really, it's a very simple concept and there's a lot of complicated jargon to get it out. So now that we have this M hat and we've defined how it works, we can see that the only way that you start in the start state for M hat, you read a word and you pop the start symbol off the stack, and then you end up in QRPS, another state. You've read a lambda, so you've consumed the whole word, and you're popping an X, whatever X may be. You can only get there, right, if QR is in F1, the final states for F1, and PS is in F2, so it's the final state for M2. You can only get there if and only if you can actually get to QR from Q0, reading W, popping Z. If you can get to QR lambda X using M1, and if you start in your start state for M2, you read a word and you end up in PS. This is the only way that this can happen because of this parallel processing. So all you're really doing is you're squashing together the transitions from M1 and M2. You're squashing together the symbols and the states, and you're just treating it as if it's one big Frankenstein machine, and you're running M1 and M2 in parallel in this Frankenstein machine. After all this, right, we've shown that a string is only accepted by M hat if it's accepted by both M1 and M2. That is, it's in the intersection of M1 and M2. So this new language, let's say L3, that's described by M hat, is the intersection of L1 and L2. And because we've generated an NPDA for this language, it is context-free. So we've shown that context-free languages are closed under regular intersection. That is, if you take the intersection of a context-free language and a regular language, you will get another context-free language. Let's go through an example, and we'll do a terrible job first, and then we'll do a nicer job. So we want to show that the language A to the N, B to the N, where N is greater than or equal to 0, and N is not equal to 100, is context-free. We can do this by constructing a bunch of different languages and taking their union. So we can take L0, which is going to be lambda, which is a word that's accepted in this language. L1 is going to be AB, which is a word in the language. L2 is going to be A2B2, which is AABB. L3 is going to be A cubed B cubed, which is AAABBB, and so on and so forth. So what we have here is 100 languages, all the way up to L99. We have 100 languages with one word in them each. These are all regular languages, and therefore they're context-free languages. And then we have everything beyond 100. And this language is also context-free. You can create an NPDA for it by counting all of the A's up to 100, and then only accepting if there's more than 100 A's. So you would have more than 100 states as you transition counting A's before you're allowed to even move on to B's or accept the language at all. So this is 101 languages. We can take the union of all of these languages, because each of these languages are context-free. We can take the union of all of them, and we will get a context-free language. Like I said, this might not be super obvious, but you can create an NPDA for this. And what you would do is you would transition from Q0 to Q1 after reading an A. Then you would push the A. Then you would transition to Q2, read an A, push an A, so on and so forth. And you wouldn't start reading B's until you were in the 101th state. And that would mean that you've read at least 101 A's. And therefore, you can create a context-free, that you can create an NPDA so this language is context-free. And so if you take the union of a bunch of context-free languages, it's context-free. This is tedious and terrible. So why don't we instead use the fact that context-free languages are closed under regular intersection to show this? So we'll use language 1, which is just going to be a finite language, A to the 100, B to the 100. So there's 100 A's followed by 100 B's. Because L1 is finite and regular, we can take its complement and we know it's also regular. So L1 complement is every single possibility except for A to the 100, B to the 100. And we can actually see that the language above A to the n, B to the n, where n is not equal to 100, is the same thing as A to the n, B to the n, where n is greater than or equal to 0, intersected with the complement of L1. So now A to the n, B to the n, where n equals 100, is not a part of this language. Therefore, by closure under regular intersection, we've shown that L is a context-free language. This is a much cleaner way of showing this. And so we have used one of our closure properties to show that this particular language is context-free. That does it for closure properties for context-free languages. There are other closure properties like complementation that I did not cover, but this should get you started. Make sure to go through some examples in the textbook to ensure your understanding is solid.